Can you hear me? Okay. Yeah, so I'm going to, as Pranav said, thank you very much for the invitation. It's an honor to be here and speaking in front of some of the people that invented the subject. So, okay, so the goal, I guess, what I'm going to tell you about is a project that's where the foundational piece is just about wrapping up, and me and my collaborators are at the stage where we're moving into applications, and I'm sort of optimistic that this perspective will find different applications in many different areas. So I'm just trying to sort of give you the overview in case this might be useful to a moduli problem that you're interested in. But the goal is to sort of take an approach to moduli problems that's just different than geometric invariant theory. So I'm going to be using the language of algebraic stacks, and so Pranav asked me to at least do a little bit of synopsis what an algebraic stack is, and I think I'm going to give an okay, just barely sufficient to understand what I'm going to talk about. But I guess sort of the goal of the theory of algebraic stacks in general, and the theory I'm going to tell you about in particular, is to sort of replace direct constructions of moduli spaces, et cetera, with conditions. So instead of saying, I constructed a moduli space of vector bundles, you say, here is something, this innate thing, which is the moduli problem of vector bundles, and it has a moduli space. You verify some conditions, and it has a moduli space. So that's sort of the flavor that a lot of the theory of algebraic stacks takes on. So I'll explain that a little bit as well. Yeah. So one of the goals is to replace these sort of classical constructions in moduli theory with conditions. And the other goal is that the kind of structures that you should be discovering are generalizing the very classical stuff, like for the moduli of vector bundles over a curve. So we're going to look for structures that generalize the moduli spaces in that example, and also the Harder-Narasimhan filtration. So the thing today I'm going to tell you about is how do you think about Harder-Narasimhan theory from an intrinsic point of view, and then in my next lecture I'll talk about how do you think about moduli spaces. Yeah. So, and in fact, yeah, so in order to make this all more concrete, I'm going to focus my lectures on a particular example called the moduli of gauged maps. So this is studied by people. It's a sort of slight modification of the moduli of vector bundles on a curve, and that will be the example throughout the talks. Okay. So that's sort of an overview. So the first thing I should say is a little bit about, so what do I, So yeah, so here it says that a moduli problem is just given by a functor. So it's, in other words, what does it mean to say a moduli problem? So a moduli problem X is a functor from schemes, and I'm going to be working over some Noetherian base scheme S throughout. I guess you could try to do more general, but that's what I'm going to do. So schemes into groupoids. So schemes op into groupoids, which looks a lot like the usual functor of points perspective in algebraic geometry, except here, of course, you have categories. So the examples. So basically, it's this moduli functor maps a scheme T to the groupoid, which is supposed to be families of objects over T. So in other words, when you're specifying a moduli problem, really you just have to sort of specify what it means to have a family of the objects you're trying to parameterize over any scheme T, and then the functoriality here just means you can pull back families along maps of schemes. And this is actually how algebraic geometers think about moduli problems anyway. So the theory of stacks is basically a formalization. There are a couple ways to try to make precise what you mean by a functor from schemes op into groupoids. So they're all equivalent, and it's all a little bit too much category theory for polite company, I mean, the intuitive perspective on this is really enough to start thinking about them. So you just say, what is a family? Yeah, so I guess, so this is a moduli, but this is a moduli functor. This is what a moduli problem should be, but mostly we're interested in what are called algebraic stacks. So this basically just means for two families. So first of all, you know, this is sort of a definition, although it'll be a little informal. So it means that given two families, so I haven't actually said what I mean by a family, but that's the point. I mean, so is this clear? Is this clear how the moduli problem is the input here? So for instance, you could say the moduli problem of vector spaces. So this was it would assign a scheme T to the group weight of vector space of families of vector spaces over T, which is the group weight of vector bundles over T, and that leads to the stack that we call BGLN. Or you could look at BunGLN, which assigns to a scheme T the group weight of vector bundles on the curve times T. So it's really not much more than that. But then you want to restrict your focus to algebraic stacks. So the conditions are that for two families, there's an object, a scheme, or and actually for us it'll be usually affine. So that's the first condition, is that if I fix two families, then there should be a scheme parameterizing the for two families over T. There should be a scheme parameterizing the isomorphism between them, and then also, and this is sort of the most important one. And yeah, usually the scheme will be affine. So in the case of families of vector spaces, this isom scheme is just a torsor for the group GLN. So it'll be affine. Okay, so yeah, and the more important one is that X admits a surjection. Oh, I forgot to say as well. So it shouldn't. The moduli problem should be a functor, but it should also satisfy a locality principle. In other words, it shouldn't just be a presheaf of groupoids. It should be a sheaf of groupoids. So I should say that also this should be a sheaf. So you should be able to glue, if you have an open cover or an tall cover, you should be able to glue objects from objects on the you should be able to glue families from families on the covering, given certain descent data. Okay, so X admits a surjection from a scheme. And so in other words, you have this general thing, which is a moduli problem. It's a certain sheaf of groupoids, and then you specialize to say this is a kind of a narrower situation. And then it looks like what I said in the beginning, was a little bit of a lie, because I'm just commenting on the previous the philosophy that I started by spouting off was that you should replace constructions by conditions, right? So here is a moduli problem. It's just a sheaf. It's just some sheaf on the category of schemes, some sheaf of groupoids. And now this looks like it's a construction that you have to do, right? What this means is that there's sort of a universal family over some scheme X. So that looks like an extra condition, but the first instance of this philosophy where constructions are replaced by conditions is what's called Artin's criteria. Which gives a very explicit and actually checkable list of conditions on my sheaf X, which guarantee it's algebraic. That's just a sort of example of a sort of instance of this philosophy. And these are checkable in many examples. Okay, so I did say I was going to make this concrete. So the example that we're going to be thinking about, which I think is close to the examples that many of you have studied, but it's a little twist that's actually never been studied before to the best of my knowledge. So this would be the moduli of gauged maps, or rather, the moduli of gauged maps has been studied, but the kinds of questions that I'm going to be asking haven't been studied. So I'm going to call this, so the setup is that C is a smooth projective curve. G is a reductive group. And X is a projective G scheme, a linearized projective G scheme. So then the stack that we're going to be studying today is sometimes called MCG of X. And what it parameterizes so it parameterizes families of objects of the following kind. So it's a G bundle. I'm going to give you what it is over a field, over a point. So it's a G bundle. Yeah, so let me fix a ground field K. So it parameterizes a curve, a G bundle. A principal G bundle. P on the curve C, plus the following data. So it's another curve, a diagram of this kind. Okay, where this map here, so this is our smooth projective curve. This is a nodal curve. C tilde is a nodal curve, and this is a degree 1 map and a nodal curve of the same arithmetic genus. So basically, so this is degree 1, same genus. So basically, what that means is that you have a smooth curve, and now this is just has a couple trees of P1s attached to various points, and this is just a map contracting those trees of P1s. And then this map U should be Kontsevich stable. P of X. Oh yeah. So P of X. So P. Yeah. Thank you. So P is a torsor. So P of X. The notation for this varies, but it's like P times X modulo G. It's the fiber bundle over the curve C whose fiber is X, and it's associated to this principal bundle. So without this bubbling, without this popping off this nodal curve here, then this would be in other words, if this is the identity, this would be just a section of this associated bundle. So I guess I should say that. So if C tilde is actually equal to C, then this is the same data of a map C to X mod G, the quotient stack. In other words, there's a map to BG, to point mod G, this map is the G bundle, and then the information for how to lift from the G bundle to a map to this quotient stack is precisely the data of a section of this associated bundle. So, yeah. And so it should be sort of clear how to define families of these things. Like a family of these things is a family of nodal curves over the base scheme T, mapping to T times C, and a G bundle on T times C. And then the same thing, a map like this that's fiber-wise Consavage stable. And with no marked points, I guess Consavage stable just means that it doesn't, this map can't contract any of the new components that have been added. There is a marked point variant, which is interesting, which is of interest in enumerative geometry, and everything I'm about to say works in that case too, but just to keep it simple. Okay. So this is the moduli problem. It's just, I mean, this has been studied without the bubbling. This is a very common thing, like, you know, Schmidt's book on decorated principal bundles. It's the data of a G bundle plus a section of some associated bundle. And then the only difference here is that you're allowing you're only insisting on the existence of a section after bubbling the curve a little bit. So I guess I should say the key property here, and the reason why we allowed the bubbling, this won't be clear until later, but I can state it now. So there's this the projection map mapping this moduli stack MCG of x to bun G is proper. Or it's actually projective. The fibers are projective Deligne-Mumford stacks. Namely, the fibers are sort of Consavage. They're sort of Consavage stable mapping spaces. They're spaces of Consavage stable maps. But this is actually the key. So you can think of this construction as a sort of compactification, a compactification relative to bun G of the space of the stack parameterizing G bundles with a section of associated bundle. Okay, so I should say I should at least remark, although I have a feeling with this audience that maybe this is a moduli problem it's already motivated, but I should say that there's a sort of motivation coming from enumerative geometry, and this is what's called gauged Gromov-Witten theory. So just to sort of say what goes on there is that there's a family. So this is the moduli problem. There's no stability condition. So the point is that there exists. Oh, and I guess I should say this has been investigated by people in the sorry, these names are listed in no particular order. So various people in communities have studied this, but the idea is that there exists a family of stability conditions. Which depend on a real parameter. And I'm going to define these for you by the middle of the talk. A bunch of stability conditions depend on a real parameter, and as delta goes to infinity, the geometry so if I impose the stability condition, you actually get a moduli space. So but the geometry of the semi-stable locus as delta goes to infinity recover as much of the Gromov-Witten theory of the GIT quotient. So there's a sort of idea, which is that maybe for reasons that I'll explain, that this moduli problem is actually a little bit easier to study than the moduli of the things that usually in Gromov-Witten theory you're studying Kontsevich stable maps of the GIT quotient. And for various reasons, this moduli problem is actually easier to study than the one that you're sort of interested from the point of view of enumerative geometry. But you can actually recover it, but only if you consider the stable locus in a large limit of this parameter. So the key words, if you're interested in this story, it's called, I guess it's the quantum Kirwan map and the adiabatic limit theorem. So these are making precise what I mean by you can recover some of the Gromov-Witten invariants. At least in genus 0, you can recover some of the Gromov-Witten invariants of the GIT quotient by studying this moduli problem. Okay, so that's sort of where this came from. Yeah, so right. So let me just dive in now to analyzing this from this framework. So the framework. So actually, what are your questions so far? Okay. Well, don't be shy. So the framework that I'm going to be discussing today is called theta stability and theta stratifications. And so the idea is that this is not the moduli of G bundles, but what if we were trying to look for an analog of the Harder-Narasimhan stratification for this stack here? That's sort of what this theory is meant to be answering. So and also yeah, I mean it's really a general framework for talking about stability and canonical stratifications of moduli problems of algebraic stacks. So the first thing, if you're trying to do Harder-Narasimhan theory, is you have to ask what is a filtration on in a general moduli problem. So what is a filtration? And actually, I learned this. I guess I kind of learned this implicitly from Carlos at some point, because the Nonabelian Hodge correspondence is a sort of filtration of a moduli space. Anyway, so what is it? So what is a filtration? So what you can actually say is that actually an equivariant. So if I take a GM equivariant bundle, on A1. So a GM equivariant vector bundle on A1 is equivalent by what's called a Riesz construction. And so if you're a graduate student and you'd like a little exercise or you want to tune out and just think about something, you can think about this for the rest of the lecture. So a GM equivariant vector bundle on A1 is the same as a map, a GM equivariant vector bundle on A1 is the same thing as a Z-weighted filtration. A Z-weighted filtered vector space. So what I mean by this, and this will sort of set some notation for the talk. So this is a finite dimensional vector space. So in my convention, this is what a filtration is. So there actually are Z many of these bundles, but because it's a finite dimensional vector space, most of these inclusions are going to be equalities, except at finitely many places. So another way to think about this. So equivalently, it's a finite filtration. So I just have to say, what are the actual bundles that appear somewhere in this sequence? Finite filtration and so in this, as you go from left, it stabilizes to 0 on the left, and it should stabilize to on the right to some finite dimensional vector space. And if you keep track of exactly where the jumps happen, where the associated gradient is non-zero, that gives you a couple integers as quote unquote weights. So this is like a family like this. So it's a usual filtration. And along with weights, So a sequence of integers like that, ascending sequence of integers, that's just recording the data of where the jumps are happening. So this gives you basically a geometric definition of what is a filtration, except that you get automatically in this definition you get these weights as well. So the natural thing that comes from geometry is a weighted filtration. And then you can do the same thing for vector bundles over a curve. I'm probably going to stick mostly to vector bundles just because it's a little easier. But basically, the same Riesz construction says that that maps. So a GM equivariant vector bundle in A1, that's just the same as a map. I said BGLN is the stack that parameterizes vector bundles. So that's just a map from A1 mod GM, the quotient stack A1 mod GM, to Bun GLN of curve. This is the same thing, is equivalent to the category of Z-weighted filtered vector bundles. So with I'll use the same notational convention for filtered vector bundles. So you can also do the same Riesz construction. You see it like that. And if you do Bun G, if you do the same with Bun G, then you get the same thing. Or you basically get G bundles. So you get a one-parameter subgroup plus a reduction, plus a P lambda bundle, basically. Where P lambda is the parabolic subgroup associated with this one-parameter subgroup. So this is the so you basically get the right answer. When you look at the moduli problems, you get the right answer for what is a filtration, except that this information of filtration encodes here the weights. In this case, for general G, this is encoding this one-parameter subgroup. So yeah.
I guess you also get a reduction to PL from the G bundle, right?
Well, it's a P lambda bundle, yeah. So if you take a fiber, if you fix the fiber, so if you fix the fiber at 1, then it's a reduction of that thing, the fiber at 1, to P lambda. But if you don't fix the fiber, then it's just a P lambda bundle, right? Fixing the fiber is like saying it's a P lambda bundle plus an isomorphism with that P lambda bundle, and the thing you get, this is the associated G bundle. Okay, so yeah, so in general, so the definition is a filtration in X is a map from A1 mod GM mapping via F to X. And the condition here, part of this interpretation is that this is a filtration of, so F of 1 is the original object, and F of 0 is what we call the associated graded. So this is the framework, and so yeah. X is any stack, really. I mean, yeah. If you have any moduli problem, you say what a family is, then a filtration of an object in that moduli problem is an equivariant family over A1. Boom. That's it. But because of this interpretation, now you can see what is the kind of structure that we're looking for. So the kind of structure we're looking for is a stratification of the moduli problem, where the strata parameterize. Well, first you have a semi-stable piece, and then the unstable pieces parameterize an object along with a canonical filtration. And now that I know what I mean by a filtration of an object, I can make sense of this in an arbitrary moduli problem. But again, because I sort of, I'd like to keep this relatable, so I'll give you one other example. So in our moduli problem, so in MCG of X, a filtration is just a filtration of the underlying G bundle. And that's essentially because this map is proper. This map P. The fact that this is a proper map over Bun G basically means that implies that a filtration in this moduli stack MCG of X is just a filtration of the underlying G bundle. So in this case, in this particular moduli problem, the sort of Harder-Narasimhan theory we're looking for is, if you have a G bundle along with one of these funny, quasi-sections they sometimes call it, does that induce for you a canonical filtration of the underlying G bundle? That's the question, to put in its most concrete terms. Okay, so let me just try to make this precise because I have. So let me give you a definition. So I've said that. So what I said in words was that you should be looking for a stratification of this stack, which parameterizes objects along with a canonical filtration. So let me give you a formal definition of what that means. Of X. So theta stratification of X, and here I'm going to assume that X, just sort of for simplicity, X is locally finite type. And affine diagonal. You can maybe do a little bit better. So it's locally finite type over this fixed Noetherian base with an affine diagonal. You can maybe do a little bit better, but this is fine. This is most of the moduli problems that come up. So a theta stratification of X is, well, it's just a collection of open substacks so I'll call these the strata SC inside so where C is in some well-ordered index set. I'm just assuming it's well-ordered because it simplifies things a little bit. So you have a collection of open substacks of this mapping stack. So I guess what I mean by this, again, this mapping stack is an example of this philosophy. So the mapping stack has a definition, which is a map from T to this is just a map from T times theta to X. That's what a family of maps should be. It's sort of the most reasonable thing you could write down. And then once you've defined that, the question is this like a reasonable object? Is this algebraic? So in order to really make sense of this, you need to know that the mapping stack is algebraic, and that's a theorem due to myself and Pregel under these hypotheses. So that's one reason why we're for this. Okay, so it's a collection of such that. Okay, so there are some conditions. So first of all, if I take the union, so I can take so any map from theta to X, I can just evaluate at the point 1. That's like the forgetful map. So such that first of all, if I take the union, right. Sorry. So the reason, so A1 mod GM plays a very important role. So I've just introduced a letter, a symbol for it, which is theta. It's supposed to be pictorial, actually, because A1 mod GM has 2 points. It has 0, and then it has a point 1, which spins all around it. So it looks kind of like a theta. That's why I call it theta. OK, so if I take the union, so I can take this evaluation map, evaluate at 1. In other words, if I take the strata, so for C bigger than for C greater than or equal to something, if I take the evaluation, so the image under these filtrations of C that lives inside of what's called the underlying topological space of X, and this should be closed. Okay, and then the other thing is that so if I consider so basically this is just saying if I take, you can think of these as these are like the these are going to be the Harder-Narasimhan strata. So these are parameterizing unstable bundles along with their Harder-Narasimhan filtrations. The C, so the larger it is, like the more unstable. So this is saying if you fix some cutoff and you throw away all the objects which are more than that cutoff unstable, that's a closed subset. So the thing you get left in the complement is an open substack. And I can ask, is Ev1, which maps SC to what I'm going to say X, I'm going to call this X less than or equal to C, which is by definition what I get when I remove. I mean, it's well ordered, so that's why. So I can basically say, OK, so I have these open, so the first condition allows me to say, OK, I have these open substacks, which is what I get when I throw everything above. And then if I take exactly C and look at the map to that open substack, it should be a closed immersion. And this is just saying that the way that the strata are ordered in the Harder-Narasimhan stratification is such that the closure of one stratum lies in that stratum union strictly more unstable strata. That's all that's saying. And then the third thing is that for any f in SC, f of 0, which I've mentioned is the associated gradient of the filtration, is in X less than or equal to C as well. So that's this fact that's this sort of fact that if you have a Harder-Narasimhan filtration, then its associated gradient is no more unstable than the original thing you started with. And this is basically the reason why you do this is because it allows you to do many inductive arguments. This says that, oh yeah, so sometimes you might see me do this in the notation. This mapping stack, I'll just call this the stack of filtrations. I'll introduce that over here. So the point is that this allows you to say that SC actually lives inside of maps from theta into X less than or equal to C. And this just as a side, you might see me do this. I call this the stack of filtered objects in X. So in other words, if the associated gradient of a Harder-Narasimhan filtration does not lie in this open substack, then you can't really identify this as living inside the mapping stack here. The fact that you can identify this living inside the mapping stack allows you to do many inductive arguments, basically. So it's basically this guarantees that this definition is stable under throwing away a bunch of strata. If you didn't have that, it wouldn't be. You could throw away strata, and you no longer have a theta stratification. So that's what 3 allows you to do. And that's like a setup for many inductive arguments. Okay. So, and I should also say, remark, there's also a notion of weak theta stratification, where closed immersion is replaced with proper and reducible, or finite and reducible. Finite and universally injective. So in characteristic 0, it's automatic that any weak theta stratification is a theta stratification, but in positive characteristic, and this is to get around like the failure of Barron's conjecture, for instance, for G bundles over a curve in positive characteristic. The structure you get there isn't really a theta stratification because those maps from the strata aren't closed immersions, they're only finite reducible.
Before you erase that, may I ask, would you say, coming to your example,
Uh-huh.
that the filtration is a filtration of the underlying G bundle, shouldn't that filtration of the underlying G bundle be compatible somehow with the...
Well, no, because that's because the X is proper. So basically, let me just draw a diagram for you. Oh, I can't cross. Okay, let me just draw a diagram for you. I'll do it right here. Yeah, so, okay, so. But there the target, there's a variant of this where the target's not proper, and then there's a compatibility condition. But let me show you something. I mean, the point is that you have MCG of X. This projects down to bun G of C. And so the question is, what is a map from theta to this? Well, it's a map A1 mod GM. So if you have a map there, you can get like this. So definitely for a filtration like this, you have a filtration of the underlying bundle. And then the question is, what is the data of the lift? So in other words, you specify the G bundle, and then you specify a lift. But I said that this map, the fibers are projective, are Kontsevich moduli spaces, so they're projective. So once you lift at the generic point, you get a unique lift over the whole family. That's sort of how it works. This is a representable proper. Yes. Yeah. I mean, it's not an essential difference. You can still study this thing when X is not proper, but then you have to be a little bit more careful because like a filtration has some additional constraints on it. But the thing that's going to make all the analysis that I tell you today so clean is the fact that it's proper. And that's the first instance of this. Maybe that's the only. Okay. Okay, so, yeah, so, oh yeah.
What is EV1 that
EV1, EV1 here is, so this is a map from the stack, from filtered objects to X, and it takes a filtration, F, just to the point F of 1. So it's just take a filtration, which is interpreting as a map from A1 mod GM to the thing, and I'm just evaluating at 1. So in other words, this is just forget the filtration. It's the obvious forgetful map. And the only other point is the 0 point, and that's passing to the associated graded. Okay, so yeah, so oh yeah, so one structure you always have. So in other words, this results in a stratification because this sort of the fact that EV1 is a locally, this saying EV1 from SC into X is a locally closed immersion on these strata. So this does result in a stratification. So, X looks like some semi-stable locus, union a bunch of strata. And then also, so I can think of the SC always fiber over something called the moduli of semi-stable graded objects. So yeah, I'm saying, but I've defined it as it's by definition an open substack of the mapping stack, but I'm saying like the way that you think about this is a stratification of X. It's just like a decomposition of X into locally closed substacks. And then also, because these are interpreted as parameterizing filtrations, you can take you can project, you can take the filtered object and project onto its associated graded, and you get what's called a semi-stable graded objects, which lives inside the mapping stack from BGM into X. So that's very much like in usual Harder-Narasimhan theory, that you have these strata, but then the strata themselves. So you can think of this as a classification problem. If X represents your original moduli problem, this decomposition is a classification result. It says that you can break it in. You break your moduli problem into pieces. You have the semi-stable objects, and then you have the unstable objects. And the unstable objects are basically determined by their associated graded, which is a semi-stable graded object, plus a little bit of data, which is in the case of bundles, it's this extension data. This is past the associated graded. I'm defining it to be sort of the image of this associated graded map inside of maps from BGM to X. So that you have the moduli of graded objects, and the ones that arise as associated gradeds of these canonical filtrations. And that turns out is also an open substack of this mapping stack. So this is like where you take a graded object and you take its direct sum and just regard it as an object again. Yeah. So this is like GUR, and this would be like the direct sum map. I mean, it's geometric. It comes from the projection of A1 mod GM onto BGM. Let's just pull back along. Yeah. Yeah. Okay. So maybe I should, because this is sort of an abstract definition, I should maybe say a word about motivation. So why isn't it enough to just define your kind of canonical filtration and then just to prove something like it's semi-continuous or something like that? Like, why is it not enough to just work a little bit more concretely? So the motivation, for me at least, was coming from, again, with so the motivation for me was called Nonabelian localization. So basically what this is it's a way to compare. Let's say I have some K-theory class. So the Nonabelian localization, it's a localization formula in K-theory. And it says that if I have some K-theory class, so let's say I have some perfect complex, so F and K naught of the stack X. So like I have some tautological, so remember this example that we're looking at is related to sort of enumerative geometry. So what we're going to want to do is impose a stability condition and then integrate certain tautological classes over the moduli of semi-stable objects, right? But what this stratification should allow you to do is it says that the K-theoretic integral, so the sort of K-theoretic index, and this is not going to be essential to the rest of the talk, so if this is not your cup of tea, then. But so basically it says that the K-theoretic index of a K-theory class on X, so this is equal to the K-theoretic index on the semi-stable locus plus a bunch of corrections of the K-theoretic index on these associated graded pieces of F restricted to the semi-stable pieces, to the associated graded pieces, tensor with something which is like 1 over the Euler class of the normal bundle. So there's a formula along this kind of, I don't want to make this precise now because it sort of would take me too far afield, but basically, if you're interested, I can tell you a little bit more about this later. But basically, there's a quasi-coherent sheaf here, which plays the role of 1 over the Euler characteristic of the normal bundle. And this is a formula saying that, okay, well, if you want to compute the K-theoretic index of something over the stack, you can. In other words, you can use this. If you know how to compute this, you can use this to compute this, as long as you know these correction terms. And the correction terms are the index of certain classes over these moduli space of semi-stable graded objects. And so this, in general, sort of gives you an inductive way to compute these numbers. Or actually, in practice, what happens is that these numbers will be easy to compute, or at least these numbers will be possible to compute. So in the example of, So in the example that we were discussing of MCG of x, so I have this map P down to bun G, and then you can say that the Euler, so the K-theoretic index on MCG of x of some tautological class is equal to the K-theoretic index on bun G of the push forward. So when you're sort of doing, when you want to integrate some tautological K-theory class over this large moduli stack, and you can say, well, that you can push forward to bun G and integrate it on bun G, and then there are these Telemann-Woodward index formulas which give you a very complete answer for what are the index of to compute index for K-theory classes on bun G. So in the actual example that we're interested in, this left-hand side is possible in certain cases to compute explicitly. And you can then use this to derive an index, the formula for the kinds of invariants that you're interested in, which are really the integrals over the semi-stable locus. That's the thing that's directly comparable to the Grove-Witten theory of the GIT quotient. Oh yeah, so I didn't say. So in order to really prove this formula, you need the correct modular interpretation of the stratification, it turns out. So if your x is singular, as it is in these cases, even when the target is smooth, the stack is going to be singular. So then you need an appropriate virtual version of this theorem, and in order to really do that correctly, you need a modular interpretation of what the strata are. Yeah.
I think I've asked you this before already, but I don't remember the answer. But is that, are we supposed to? I think the answer was no, but anyway, are we supposed to think of this as an Tia bot type of formula?
Yeah, I mean it's sort of related, but this is like in K theory, not in cohomology. But yeah, it's very similar. Yeah. I mean, this is like saying, yeah, the T-Bot formula says that the cohomology is additive under these stratifications, and then there's other theorems that say that the derived category is additive in some sense under these stratifications. And so this is like a statement about this is Arham from O to F in the derived category. So this is making some sort of, but actually this is much simpler than that, because this is actually just a local cohomology computation, really. The reason why the stratification becomes necessary is because in general this thing will be impossible to make sense out of this thing. The correction, basically, if you have a generally, even if you're on a projective variety and you have a closed subvariety, the local cohomology sheaf is going to be quasi-coherent. It's going to be enormous. So that's not really good for computing indexes because you want finite dimensional things that have finite dimensional cohomology. So it's sort of miraculous fact about this stratification that won't be the case here, and that you can make sense of these correction terms, and everything's a finite formula. So that's really, but it's simpler than all that other stuff. Okay, so all right, so I guess what I'd like to say is the following. So that's the motivation. So the question is, where should the stratification come from? Okay, so I'll give you a definition. So a numerical invariant on X is 1 to any so I should say non-degenerate. So it's any non-degenerate map from BGM to the n into X, it assigns a function. So it's a real valued function, scale invariant. So for any, and what this is a z to the n graded object. So a numerical invariant is some rule which anytime you have a z to the n graded object, it spits out a scale invariant function on Rn. And then this should be compatible with restrictions in the obvious sense that if you have if I have a map from tori from a lower ranked torus, an injective map of tori from a lower ranked torus into here, I can restrict I can compose, and that should be the same as the restriction of this function to that lower dimensional subspace. So it should be compatible in all the obvious ways, and then it should also be locally constant in families. In other words, if I have a family of graded objects, so a map from this times BGM to x, then this value of this function should really be sort of locally constant. So I should say, so I'll just write locally constant and compatible with restriction. What? Well, I mean, actually, no, I mean, this is a coordinate thing, but it's the Lie algebra of the torus. It's the co-character lattice of this torus tensor with R. Is how you should think about it. Yeah, I mean, in particular, if you have just BGM, this gives you a scale invariant function on the on R minus the origin, and that's basically just two numbers. I mean, you can think of this as literally a function which assigns a map from BGM. So if you take BGM to x, for every graded object, you get a number, which you just evaluate the function at the point 1 or any other positive point. So this really gives you a function on the set of graded objects that's locally constant in algebraic families. Okay. And then there's a third condition, which is not, I guess it's not strictly necessary, but it makes the statements of the theorem I'm about to tell you easier. So, let me just, for the purposes of this talk, so we'll assume that mu sub g is what they call strictly quasi-concave. Which just means that if you're, so you have this function on R2 minus the origin, and if you take any line segment along here, the function looks like that. In other words, what it means is that the preimage of any, of the set on which the function has values greater than or equal to c is convex. That's what the definition of quasi-concave means. So it basically means that along any path here, if I look at the value of the function, it looks like that. Oh, I meant, yeah. And then also, plus on any, I guess, what did I say? Yeah, so on any rational polytope in Rn minus the origin, the max, so max is achieved at a rational point. Oh, I should say, and I've said that it's scale invariant. So to say that this is strictly quasi-concave is kind of a lie, because if you go radially, it's constant. So it's not strictly quasi-concave in the radial direction, but any other direction it should be quasi-concave. It should basically I'm thinking of this as a function on Rn minus the origin modulo scaling, which is a sphere. And so basically I'm saying this is a strictly quasi-concave function on the sphere. Okay. Okay, so that's something. Where does it come from? So in this example, in the example that we're talking about, oh wait, let me just say, yeah, so if you have a numerical invariant, then you can say that a point P in X is unstable if there exists a filtration. So if there exists a filtered object with f of 1 isomorphic to P and mu of f, so mu of gur f with its canonical GM action is bigger than 0. So to any filtration, I can sort of restrict to the origin, and that's an object with a canonical GM of automorphisms. And so this, what I just mentioned is that this is really supposed to give me just a number. So I can take the mu and get that number out. And this number should be, this is a real number. And it should be, if it's bigger than 0 for any filtration, that's unstable. So this is an intrinsic formulation of the Hilbert-Mumford criterion in geometric invariant theory, if you're familiar with that. Okay, so I'm going to do the, yeah, I was debating in my head whether or not to give you the definition first or to do the example, but I figured you might as well just see it. This is the definition. So the example here, this is in MCG of x. So mu, the function mu is equal to, so 1 over, so I guess 1 over b. So I mean, yeah, so let me say this. So mu is equal to 1 over b times L sub bun g, or bun GLN. Let me just do GLN, because I can write down the formula, plus delta times Lx, where, so L bun GLN, so in other words, if a filtration, so I'm saying, if given a filtration f, the value of mu on that filtration is this function. So in other words, that I'm sort of saying you can evaluate on this function, you can evaluate mu on any filtration, you get a number. So what number is it? So if f is the filtration that looks like EW plus 1, EW, etc. So remember, going back, that a filtration in this thing is just a filtration in bun GLN of the curve, and so that's just a z-weighted filtration of the underlying vector bundle. So what are the numbers? What are these functions here? Well, they're actually going to be L bun G. In this case, is just the number. I think there's a minus sign. Yeah, no, it's just sum of W in Z times the degree of GER W of E minus D over R times the rank of GER W of E, where I should explain that D is equal to the rank of the D and R are degree and rank. So R is really N, it's because I'm in GLN, so let me just put that here. So N is the rank of the full bundle, and then also, and the degree, the D is the degree of the thing that this thing stabilizes to. So you have the rank and degree of the underlying bundle, and then you have this number that you construct from the filtration with the weights. The key thing is that this is a function of the weights. So Lx, so if you have one of these objects, you know, it's a picture like this. And this thing actually maps to sort of x. So, well, anyway, basically, at the generic point of the curve, this is actually literally a section. So generically on the curve, this is really a map to the quotient stack x mod g. So Lx, then you're sort of in a GIT situation. So I'll just say that Lx is equal to the Hilbert-Mumford weight. So in some sense, generically on the curve, you can really identify this as a point in X and a one-parameter subgroup under which that point has a limit, and then you just take the Hilbert-Mumford weight there. So I fixed I think I said this in the very beginning, but X is already a polarized G action. So underlying this, I fixed a line bundle on X, an ample line bundle. And then finally, B is just equal to the sum over W of W squared times the rank of GER W of E. So the important thing is that this as a function of the weight. So if you fix, so remember I said that this is really the data, this filtration is really the data of a finite filtration. Plus some weights. So this is some number associated to any filtration of this, any weighted filtration. And if I think of this as a function of the weights only, so I fix the underlying the underlying filtration of the vector bundle, then this is a linear function in the weights. This is going to be like a piecewise linear function in the weights. And this thing is going to be a quadratic form in the weights, a positive definite quadratic form. And so this function here ultimately is a sort of piecewise linear thing divided by a positive definite quadratic form. And there's a sort of a theory of optimization of these things that's quite explicit. You can really just compute on any, if I fix my filtration and ask what's the maximizer for the maximizing choice of weights, you can find that for any fixed filtration. So it's going to be important. Okay. Which condition? Oh, yeah. I mean, basically, this is like it's not too hard. It's not too hard. It's like the normalization of some sort of convex thing. Yeah, it's okay. Yeah, that's not too hard either. That's like the part of this theory of optimization and stuff. It's the same. Yeah, it's the same. Yeah, it's Mundet. This is Mundet stability. This is the numerical invariant for Mundet stability, if you're familiar with that. Yeah, so in general, I should say that what the formula is in general is mu is, so in general, what you have is a line bundle. This is sort of a typical place where this is coming from. So you have a line bundle, L on X, and what this formula is, and B is actually a class. Okay, so I'm not going to. Let's just imagine you're over C, and I'm just talking about like the de Rham cohomology. So basically, there's some data which you need, which is a norm on, quote unquote, norm on one parameter subgroups. That gives you this. Oh shoot. Yeah. So you need this because part of this is linear and this is linear. So if you scale if I just rescale the w's by a positive number, this is going to increase the numerator, homogeneous of degree 1, and it also decreases the denominator, which is homogeneous of weight 1, because I have the square root there. So that's why this is a scale invariant function.
If it's on a sphere, how can you have a convex function on an entire sphere?
Yeah, what I really, because this convexity condition applies for line segments which don't go through the origin, because the origin is not in the point of the original space. And so, like, if you have a line segment that doesn't go through the origin, it's contained in a hemisphere when you project it onto the sphere.
Yeah, but isn't your function going to be convex on the sphere? I mean, how can you have a convex function on the sphere?
It's not. I mean, I'm saying it's only locally convex.
But even locally convex.
Yeah.
There's no condition on
I don't.
weights or something like that?
I don't. What? So. No, I don't think so. Is there? I don't think there's. I think maybe. Yeah. Sorry. Maybe I. I think it should be. Yeah. Sorry. It should be. It should be strictly quasi-concave on the locus where mu is bigger than 0. Okay. Yeah, I'm sort of not so interested in the negative things because those are never going to be destabilizing. So I'm really only considering the mu bigger than 0 piece. Yeah. I mean, in practice, where it really comes from is a convex, it really sort of comes from a sort of rescaling of a convex function. Well, that's, I'll get to that. Yeah, typically it comes from a convex function on Rn itself. Okay. So the formula, the sort of general formula here is that you have a line bundle on X, and what I do is I take the pullback, so I have my filtration, which is a map from theta to X, and mu of the filtration is equal to F star of C1 of the line bundle divided by the square root of F star of B. And so to interpret this, so this up here lives in H2 of theta, which is with rational coefficients, which is Q, and this thing lives in H4 of theta, which is also Q. The class down here. So in other words, I just pull back and I use the fact that I know the cohomology is just one dimensional in rank 2 and rank 4, and I can write down this formula. So this is where the formula comes from. It comes from the determinant line bundle. So this comes from if you take the determinant of the cohomology, the adjoint representation for GLN, you sort of get this, or something that's proportional to it. This comes from the GIT line bundle. Although actually this thing here is not actually technically from a line bundle in the stack, as far as I know. But it's just but typically that's where it comes from. And then you write down this formula. Okay, so the question here that I've been sort of dancing around is does there exist a maximizer? So does this, so question, does there exist a Harder-Narasimhan filtration? So for an unstable P in X. So what this would be is a filtration. So a filtered object of X plus an isomorphism in other words, so it's a filtration of the point P such that mu of F is equal to the sup. What I'll call this function M mu of P, which is, I'll define this to be equal to the sup over all filtrations. Of mu of F. So in words, a Harder-Narasimhan filtration would be a filtration which maximizes, with an isomorphism like this, which maximizes this numerical invariant among all possible filtrations of this object. So this actually is not, this is not the classical way that they define that Harder-Narasimhan define their filtration. This is a reinterpretation of that, and it's a little bit surprising. I mean, this is just some number, and what this is saying, it's a vastly infinite kind of optimization problem because there's so many different kinds. Literally, the isomorphism classes of filtrations is sort of has the same kind of cardinality as the ground field, and then also you have all these assigned choices of weights. So this is saying that among all possible filtrations and among all possible choices of weights, is there a unique filtration and a unique choice of weights that maximizes this function? And because this is the numerical invariant is invariant under scaling, rescaling the weights, this will only be a maximizer. So this will be unique up to rescaling weights. And you could also ask, so this is question 1, is like, does there exist Harder? And the question 2 is, does this define a theta stratification? In other words, if I choose if I say I consider all filtrations which are Harder-Narasimhan filtrations of their associated of the underlying object, that gives me a subset of the mapping stack. I have to up to rescaling the weights, but let's just. And does that actually give me a theta stratification? in the sense that I defined for you. And so let me say there are sort of two properties that you would, if this is going to define a theta stratification, there are two things that you would want to be true. So first of all, so two conditions. So one, oh, sorry, let me label them. So there's condition B, which is a boundedness condition. So basically what this says is that, okay, so this is an optimization problem. I'm saying there's a number associated to any filtration. I'm trying to look at all filtrations and see if there's a maximizer. So, but if this is going to give you like a stratification, then over any finite type scheme, only sort of, only finitely many Harder-Narasimhan types are going to appear. So basically it says that if you're trying to do this maximization problem, the condition says if you're trying to solve this maximization problem for all the points in some bounded family, it sort of suffices to only go boundedly far out into the stack. So to say, so let me say this in words and symbols. For all finite type T and maps, so for any family over finite type scheme, there exists a bounded substack x prime such that, and then I guess in symbols, I'm always, so such that for all f in So in words, if you have a filtration which is destabilizing for some point, for some fiber in this family, and it suffices to only work with finite type points. So for all filtrations that are destabilizing for some fiber in this family, there exists another filtration with f prime of, so there's a filtration of the same point with a larger, a greater than or equal to numerical invariant, and gur of f prime is in x prime. So that's written, it's a sort of a dense, logical statement to unpack, but basically it's just saying that if you have a family over some finite type scheme, then you can identify some sufficiently large but bounded open substack, some sufficiently large but bounded substack, such that for any possibly destabilizing filtration, I can find another filtration of the same object whose numerical invariant is greater than or equal to the one that I started with, and where the associated graded lies in this bounded substack. And this tells you that you don't have to look. You can sort of, we'll see how this works in this example in just a moment. What?
What is bounded subset?
Oh, bounded means it's in the image of some family over a finite type scheme. So you can say it's contained in some quasi-compact open substack, for instance. What? That's bounded. Bounded is sort of an older terminology in the moduli literature. I mean, yeah. Okay, so this is the kind of condition that you need. So notice also if x itself is bounded, if x is quasi-compact, then this condition automatically holds. Because you could just take x prime equal x here. So this is really only an issue for these very large moduli stacks that are really very interesting. And then there's another condition, which is specialization. So this is sort of the kind of thing, this is a sort of family version of the kind of thing you'd need to solve 1, to find a Harder-Narasimhan filtration. And then to do 2, does it define a theta stratification? Well, you'd want some sort of thing that says, just like the Harder-Narasimhan filtration for vector bundles, if you have a family over a DVR, then the sort of special fiber is more unstable, at least as unstable. The special fiber is at least as unstable as the generic fiber. So you can formalize this. This says for all DVRs, R with residue field K and fraction field capital K. And so, yeah. And for any maps, so for a family over this DVR, over spec of this DVR, so for any kind of setup like that, you have a family whose generic fiber is unstable. If Fk is a Harder-Narasimhan filtration, for psi k, then so this is saying that remember this function m mu, this is like the soup over all possible filtration. So this is like measuring the degree of instability. So this is just saying that the special fiber is at least as unstable as the generic fiber, and if equality then F extends to a filtration of psi over the whole DVR. So these are two things these are two features of the Harder-Narasimhan filtration for vector bundles. This sort of boundedness and then this specialization thing. So this is saying that if the special fiber has exactly the same degree of instability, then actually you can get a family of, you can extend the Harder-Narasimhan filtration in the family. So the theorem so the main theorem says that if X is finite type algebraic, affine diagonal, oh sorry, not finite type, locally. And mu is a numerical invariant then mu defines a theta stratification. If and only if B and S hold. So yeah, so in other words, these two conditions that you sort of think about trying to reflect the nature of the Harder-Narasimhan theory, it turns out that those are necessary and sufficient. So that's the main theorem. So the boundedness actually does just imply the existence of Harder-Narasimhan filtrations always. And then this specialization actually implies all the other. The boundedness and the specialization together imply all the other things. Okay, so, and I guess the theorem 2. So this is sort of, yeah, this is, I guess, this is started in my thesis, and then it's been a very long project. It started in my thesis in a much more specialized case, and then slowly I was able to peel off over many years. I was able to peel off hypotheses and hypotheses, and then the paper just kept getting longer and longer. And now the paper is very long, but there are very few hypotheses. So I don't know. I guess that happens, but anyway, that's the final. That's like the final. What?
What is weak Theta stratification?
Oh yeah. So the weak. This is the thing. If you're not in characteristic 0, if you're in characteristic 0, you can just ignore this. If you're not in characteristic 0, then you have this issue that the maps might not be closed immersions. They're just going to be proper and radicial. So like for instance, the usual stratification for Bun-G over a field of characteristic P is not always a closed immersion. If you interpret it, it's sort of equivalent to the Barron's conjecture, if you're familiar with that. So Barron had some vanishing of certain cohomology, the adjoint bundle, and that is actually equivalent to these maps being closed immersions. But in this case, in sometimes they're not. Yeah. Anyway, but you can just ignore it in characteristic 0. So the theorem, and this is due to myself and Gonzalez. Oh, wait, let me get do the thing. Yeah. Oh no, Gonzalez first. Is that these conditions hold on this moduli stack that I was telling you about. So in other words, the answer is yes for this stack. You do have a Harder-Narasimhan theory, and it's sort of an interesting thing because so in other words, just to state it again, if you have a G bundle on a curve and a sort of quasi-section of this associated X fiber bundle, that gives you a canonical filtration of the underlying bundle. But the filtration is not convex. So this is for any delta. So when delta is very close to 0, I've sort of erased the thing, but the formula for this was L Bun-G plus, maybe I forgot to put delta in there. Did I can't remember. Anyway, it's L Bun-G plus delta Lx divided by square root of B. So when delta is very close to 0, this just looks like the stability function for Bun-G. So for delta very close to 0, you're just basically getting something that's converging to the Harder-Narasimhan filtration. But unfortunately, for the comparisons to Gromov-Witten theory, you're looking at the limit delta goes to infinity. And in that case, you imagine that the Harder-Narasimhan filtration that you get from this is being pulled closer and closer to the Kempf-Ness optimal destabilizer for the generic point of the for the generic point. So for delta large, sort of X, the stability on X is playing a much stronger role. But in particular, the actual filtration that you get is no longer convex. It's not like I don't know of any way to prove this in the usual, the quickest way to do Harder-Narasimhan filtrations for in the Nonabelian categories, you find like a maximal, like what Carlos was saying, you find a subobject, maximal subobject of maximal slope, and then you do the quotient, et cetera, and you're really making use of the structure of an Nonabelian category. But in this case, that's not really going to work for you because the filtration has no particular structure. It's just some canonical filtration. So yeah, so I guess I'd like to. This is so nice. I have another lecture. So I'd like to tell you a little bit about how this is proved, because I'm sort of running out of time, right? Yeah. Oh, 1 minute. Yeah. So I'd like to tell you a little bit about how this is proved, but then I guess I'll do that. I'll go into that in my next lecture, and then and I also want to talk the second part of this story, which basically, so this is all like, how do you get a stratification? The second kind of feature that you'd like to capture in this general framework is the existence of moduli spaces or constructing moduli spaces. And as I said before, like, you don't want to construct a moduli space. You have this beautiful stack. You have a notion of semi-stability. And the question is, does there exist a moduli space? And so what you really want are conditions for the existence of moduli spaces. So that's what I'm going to tell you about next time, is some ways, if you have an algebraic stack, how do you know, how can you identify, so in a a very checkable criterion for whether or not you have a moduli space. And we'll see it also how it works in this example. Yeah, okay, so that's all. Thank you.